Hello, Professor Sargent here with you again for another Math 101 flipped classroom lesson. This is on section 10.5, and we're going to take a look at two very special bases and using them with logarithms. The first of these bases is base 10. It's also referred to as the common base because it's so important. When we work with logarithms in base 10, we leave out writing a base. That is the common log. Common log is base 10. And our second important base is called the natural base, or base e. E is an irrational number, just like square root of 2 or pi. If you've ever worked with financial applications, compound interest, this would be, if we look at this table, looking at the right-hand side, if you had interest being compounded on $1, and the interest rate was a ridiculously high 100%. 100% as a decimal would just be 1. Let x be the number of times per year that interest is being compounded. What we're seeing here is the more often that interest is being compounded, on the right-hand side, these numbers keep going up, but they are leveling off so that each time it goes up by a little bit less, so that it's closing in on a particular number. And this leads us to seeing the base e in continuous compound interest problems. It also shows up in biology with population growth, or in chemistry with decay of radioactive elements. So the calculator has an approximation like what we see for e at the bottom. So when we refer to logarithms in base e, we write that as ln of x. That stands for the natural log. Why don't we put nl instead of ln? Probably because some other country is where the person who came up with natural logs first lived. I think it's Logarithms Naturalis or something like that. All right, so anyway, common log, base 10, we just don't write a base. And the natural log, base e, we write ln of x. You wanted to see some examples where we use a calculator to approximate the values of common and natural logarithms? You got it. All right, number one has three different parts. Only two of them are showing at the moment. In the first one, we're looking for the log of 109. When the base is not written, we're talking about the common logarithm, base 10. So that's really the log of 109, base 10, and the calculator already has that. Your calculator may have it in a different spot. Log of 109, close the parentheses. To four places, that is the 10,000ths place. And after the fourth place, in the fifth place is a 2, so we're going to round down. We're going to round that down to 2.0374. Now, a few points here. Since that was base 10, that means that 10 to the 2.0374 power should be approximately 109. I'm not putting the equal sign, I'm putting the squiggly approximately equal sign here because we rounded the answer to 2.0374, and so we're not going to get exactly 109. So if we take 10 to the 2.0374, we're going to get something really close to 109. In fact, that is less than 1/100th away. Since that's smaller than 109, I'm taking that answer away, 0.066 something. Whereas if we had looked at what was after the 4 and rounded in the wrong direction, the 2 was after the 4. If we had rounded that up to 2.0375, check out what happens. You should get something that is further away from 109. So take 10 to the 2.0375. That is a little more than 1/100th away, whereas the other was a little less, 0.0066 something. A few more points. Since 10 squared is 100, then we should have expected that this would be an answer close to 2. Why close to 2 instead of 3? Well, 109 is close to 100. 10 cubed, that's 1,000, something far higher than 109. Also, the 109, in some textbooks, they call that the argument of the logarithm because of the relation of logarithms and exponents. I've also heard the 109 referred to as the anti-logarithm of the 2.0374 in base 10. Now, this next one, 5.86 times 10 to the 7th, that's kind of a big number, but not something so large that the calculator can't handle. Move yourself out of that exponent and then close the parentheses. Rounding that to 4 places. Going to the 10,000ths place, we've got 8, but then that 9 right after it, we're going to round that up. So 7.7679. I'm going to show you another option here. Since we have multiplication inside, we could write that original logarithm as the log of 5.86 plus the log of 10 to the 7th. Since the common log is base 10 and 10 to the 7th, something exponential in the same base, it's going to cancel out. So we just have the log of the 5.86 plus 7. So log of 5.86, close the parentheses, and then add the 7. Same result. Maybe once in a while we would get slightly different answers way far out, but much past the 4 places that we rounded to. You do the same thing I did for the previous question and check that when we raise 10 to this power, that would equal the argument or the anti-logarithm 5.86 times 10 to the 7th. And why did I even bother using the product rule for logarithms to split that up as a sum of separate logarithms? Well, what if that had been 5.86 times 10 to the 999? It's a number too large for the logarithm to handle. So let's clear that. Well, it's a number too large for the calculator to handle, even if I had put the log first. Since it can't deal with the argument inside that logarithm, then it's not even going to be able to take the logarithm. And then our last for number 1, to estimate the natural log of 0.8903. As a side note, the natural log of 1, or the log of 1 in any base, is supposed to be 0. Then, since we're dealing with an argument that's smaller than 1, I'm expecting an answer that is negative. Natural log down here is right underneath. Natural log is right underneath the common log, put in the argument of 0.8903. I do get an answer that is negative, as I expected. 4 places out, the 10,000th place. There's a 9 after that in the 5th place, so that's going to round up. The way you round, that would be regardless of the negative sign. 0.1162. And to check that, when we're talking about a natural log, our base is e, which happens to be right above, not the next button up, but you use the second, like a shift key on a typewriter or computer keyboard. Put in the negative, not a minus sign, but a negative. 1162. You should get something close to 0.8903. And in this case, this is very nice. We rounded our answer to 4 places, and then when we round the argument or the anti-log to 4 places, that 9 is going to make that go up to 0.8903. A lot of calculators only work with the common log and natural log, base 10 and base e, respectively. Or if they can work with other bases, it takes more work to get to them, more buttons to push. So that it's better to know the following change of base formula. We start out with the log of x in base a is equal to m. That could be any base. Rewrite that as an exponential expression. The answer to a logarithm is an exponent, so that m is an exponent for the base a. If we take the logarithm in a new base, b, on both sides, we've learned that we can bring an exponent out in front, and then if we divide both sides by the log of a in base b, we get the following rule. And why we did that division is because we wanted to know what the log of x in base a was equal to. We named it m, so we've isolated m in this case. What this is saying is that whatever you were originally looking for, log of base a, we could take the log of the same thing, x, in the base b, and divide it by the log of the old base in the new base, log of a base b. And how that is useful? Well, in particular, because calculators have base 10, the common log, and base e, the natural log, then regardless of what your original base a was, as long as it's an acceptable base, you can calculate the logarithm of x base a either of these 2 ways. You're going to come up with the same thing. In number 2, this also has 2 parts. Supposed to use the change of base formula to estimate each logarithm, again, to 4 places. Now, if someone asks, I could give a general proof of the change of base formula, but I'm going to verify that it works for this question. We could say that whatever that is going to equal, call it x, then because the answer to a logarithm is an exponent for the same base, in this case 8, then 8 to the x equals 288. you take the logarithm of both sides, whether it's the common log or the natural log, the calculator is going to be able to deal with that. Do that to both sides. Then we have the power rule that lets us bring that exponent out in front as a factor or a coefficient for the logarithm. Since the only thing that's happening to x, whatever log of 8 is, it's a number. And although it's written behind it instead of in front of it, still, it's some number times x. To get x alone, you would divide by that number being multiplied to it. The change of base formula in words is telling us, take some new base. Take a base that the calculator can work with. The common log, or base 10, or the natural log, i.e. base e. Take the logarithm of the same argument in the new base, divided by the log of the old base in the new base. So, taking the log of 288 divided by the log of the old base 8. Rounding that to 4 places, the 0 is going to make that round down, so approximately 2.7233. If you would use the natural log instead, take the natural log of 288 divided by the natural log of 8. And I've cleared out what we had before, but at least when we round to 4 places, we are getting the same thing. Again, I did not give a complete proof because we would have had to have any acceptable argument and any acceptable base to translate over to something like this. Again, if you would like to see a complete proof of the change of base formula, why it is actually true, let me know. Once you know it, though, you can apply it whenever you have some other base that the calculator can't handle. For this last one, we're supposed to approximate, still to 4 places, to approximate the logarithm of the 4th root of 3 in base 9. And I'm going to use the common log, but again, like we saw in the last example, you could use natural log in both the top and the bottom. I showed that in the previous example. I'm going to leave it to you to check it on this example. Remember, in the numerator, you're taking the log of the old argument, same argument, divided by the log of the old base. Now, to get the 4th root of 3 in the calculator, I'm going to put that in as 3 to the 1/4 power. So here we go. Log of 3 to the 1/4 power. Notice how I've been putting parentheses afterwards before my next step. I had to scroll to the right to get out of the exponent before I do that. I'm dividing by the log of the old base, the common log of the old base. And coming up with 0.0125. If your online homework system gets snippy about it, since it's set to 4 places, on this one you have no rounding to do, but you might have to tack in a 0 at the end. Well, that looks suspicious, the fact that it terminated. Whenever you get a decimal that either terminates or repeats periodically, like 0.38, 38, 38, something like that, that should be a decimal that is rational, something that you could write as a fraction. So to check this, even though it was not the intent of the question, still, notice how I rewrote the 4th root of 3 as 3 to the 1/4. So what if I had applied some properties of logarithms that we know? Could use the power rule to bring the 1/4 out in front of the logarithm. And what power of 9 will give us 3? Well, 3 is the square root of 9. So in other words, 9 to the 1/2 power will give us 3. And the answer to that logarithm is an exponent. So 1/4 times 1/2, multiply straight across to get your new numerator, your new denominator. There is no reducing that we can do. If we check out that 1/8 on the calculator, that's going to equal exactly the decimal that we came up with. 1 divided by 8 is 0.125. So when I circle here, that's the answer they wanted. Something directly put into the calculator, but the work I've shown down here confirms it. And that's all for now. Here we're asked, what does the function predict for the percent of outpatient surgeries in 1996? X is counting since 1900. So we should be putting in 96 for X. And when we do that, already going to be giving us a number that we're supposed to interpret as a percent. We're supposed to round that to the nearest percent. I'm not going to round at any point until the very end. Natural log of 96 is 4.56 something. Multiply that by 303. And then add 1,312. Coming up with about 2694.997502. That would round to about 2695. I misread something there. That 1,312 is supposed to be negative. So luckily I did that one step at a time. After multiplying by 303, I had about 1,382. I'll take away that 1312, that'd be the same as adding a negative. That's coming up as about 70.997502, which would get rounded to 71. Again, you don't do any conversion here. That's already supposed to be thought of as a percent. Second part, when did the outpatient surgeries reach 25% to the nearest year? Now this is going to be algebra. Again, not converting, f of x is already supposed to be thought of as a percent. So 25 equals negative 1312 plus 303 times the natural log of x. Add 1312 to both sides. You get 1337. Yeah. Divide by 303. Don't do any rounding yet. Natural log of x is approximately 4.41254124. All right. Now, remember the answer to a natural log is an exponent, and the base of a natural log is the natural base e. So if you take that answer as a power for e, then we're getting 82.478796.99. That 4 is going to round it down to 82. And remember, x is the number of years since 1900. So after that rounding, add that to 1900 to get 1982. And that's all I've got for now. I hope this has helped, and I'll see you in the next one.